Most computer memory, like RAM, is volatile. This means it requires a constant flow of electricity to hold onto information. If power is lost, the data vanishes. In contrast, SSDs use NAND flash memory, which is non-volatile. Even when the power source is cut, the electrical charge trapped within the microscopic cells remains locked in place. This permanence is why your files and operating system remain intact even after you shut down your computer, making it the foundation of modern high-speed storage. At the heart of every SSD is the memory cell. This microscopic transistor acts like a gate that can trap electrons. When we charge this gate, electrons are pushed inside and held there. This presence of electrical charge represents a binary 1. Without this charge, the cell represents a binary 0. The gate remains empty, and the SSD reads this as an off state. By rapidly toggling these millions of cells between charged and discharged states, the drive stores all of your digital data. At the heart of every NAND flash cell lies the floating gate, an electrically isolated structure that acts as a permanent storage vault for data. To write data, we apply a high voltage to the control gate. This creates an intense electric field that pulls electrons out of the substrate. Through a process called Fowler-Nordheim tunneling, these electrons force their way through the insulating oxide layer, effectively tunneling into the floating gate. Once trapped inside this amber-colored floating gate, the electrons stay there even without power, locking in a specific binary state. By measuring the electrical charge of this gate, the SSD controller can reliably determine if the cell represents a 1 or a 0. In a solid-state drive, data is written by manipulating the voltage threshold of a memory cell. By applying a high voltage, we force electrons to jump through an insulating layer onto a floating gate. Watch as the voltage surge pushes these electrons through the barrier. This process, called quantum tunneling, traps the electrons on the gate, changing the cell's electrical threshold. This trapped charge represents a binary 0. Because the electrons are stuck behind the insulator, they stay there even without power, allowing the drive to retain data without any physical movement. To clear the bit back to a 1, a reverse voltage is applied to pull the electrons off the gate. This reset cycle clears the cell, preparing it to hold new data. In SSD technology, we increase capacity by packing more data bits into a single memory cell. This is achieved by defining distinct voltage levels within that cell. The SLC architecture stores 1 bit 2 levels. As we add more bits, the cell requires finer voltage control to distinguish between these increasing states. The MLC architecture stores 2 bits 4 levels. As we add more bits, the cell requires finer voltage control to distinguish between these increasing states. The TLC architecture stores 3 bits 8 levels. As we add more bits, the cell requires finer voltage control to distinguish between these increasing states. The QLC architecture stores 4 bits 16 levels. As we add more bits, the cell requires finer voltage control to distinguish between these increasing states. The PLC architecture stores 5 bits, 32 levels. As we add more bits, the cell requires finer voltage control to distinguish between these increasing states. Adding more bits increases storage density significantly, but it shrinks the voltage window. This makes the data harder to read, slowing down performance and reducing endurance. The SSD controller acts as the brain of the drive, orchestrating every operation. It is a highly specialized processor that manages the complex task of data storage. When data arrives, the controller uses logical block addressing to map incoming requests to physical locations within the NAND flash memory, ensuring data is stored efficiently. Beyond mapping, the controller coordinates read and write operations, manages internal housekeeping, and maintains the drive's overall performance and integrity. Without this sophisticated controller, the millions of individual memory cells would remain unmanaged and inaccessible to your computer. NAND flash memory has a limited lifespan. Every time we write data, the memory cell degrades slightly. If we always wrote data to the same spot, that area would fail very quickly. To prevent this, the SSD controller uses a process called wear leveling. It tracks which cells have been used and intelligently distributes new data across the entire chip. By spreading wear evenly, The controller ensures that no single cell is prematurely exhausted. This extends the lifespan of the entire SSD significantly. SSD memory is organized into blocks. Over time, some data becomes stale, meaning it is no longer needed but still occupies space. Because SSDs cannot overwrite data directly, they must perform garbage collection. Valid data is identified and moved to a fresh block. Once the valid data is safely moved, the entire original block is erased, reclaiming the space for future write operations. This process is essential for maintaining high write speeds and ensuring the drive's longevity. Traditionally, memory cells were arranged side by side on a flat or planar surface. However, shrinking these transistors further leads to interference and reliability issues. To store more data, manufacturers had to innovate. Instead of building out, they began building up. 3D NAND stacks memory cells in vertical layers, much like an apartment building. This vertical stacking allows for massive increases in storage density within the same tiny physical footprint. By adding more layers, we can pack hundreds of gigabytes or even terabytes into a single chip. This revolutionary architecture is the foundation of modern high-capacity solid-state storage. In traditional SSD designs, the memory storage array and the logic circuitry that manages it sit side by side on the silicon wafer. This takes up valuable space. CMOS under array, or CUA, revolutionizes this by stacking the logic circuitry directly beneath the memory array. This maximizes wafer efficiency. By shortening the physical distance between logic and memory, we significantly improve performance efficiency, allowing for faster data throughput and smaller device footprints. This vertical integration is a key driver in modern high-density NAND scaling, essential for the high-performance AI workloads of tomorrow. The SSD controller connects to the CPU through the PCIe interface, which serves as the primary data highway. PCIe 6.0 doubles the bandwidth capacity of its predecessor. By utilizing advanced signaling, PCIe 6.0 enables massive data throughput, allowing the drive to communicate with the CPU at speeds reaching 30 gigabytes per second. This unprecedented speed eliminates bottlenecks, ensuring that high-performance storage can keep pace with modern computing demands. Traditionally, to search or filter information, an SSD must send massive amounts of data across the interface to the main system CPU. This constant data movement creates a major performance bottleneck. Computational storage solves this by making the SSD smarter. By integrating a dedicated processing unit directly on the drive, the SSD can filter data locally. Only the relevant results are sent to the CPU. As we push for higher storage density, we enter the era of penta-level cell, or PLC storage. This technology packs 5 bits of data into a single memory cell. To store 5 bits, the controller must distinguish between 32 discrete voltage levels. These levels are incredibly close together, leaving almost no margin for error. The endurance challenge arises because memory cells naturally degrade over time. As electrons leak from the charge trap, the voltage thresholds shift. In high-density PLC storage, this slight shift causes states to overlap. Once the controller can no longer reliably identify the specific voltage level, the data is lost. This physical limit is why endurance drops as we increase bits per cell, necessitating advanced AI-driven error correction to stay functional. As memory cells age, their ability to hold a precise electrical charge decreases. In a new healthy cell, the gap between a binary 0 and 1 is wide and clear. Over time, wear creates voltage noise. The threshold becomes dangerously narrow, making it difficult to distinguish data accurately. Modern drives employ AI-driven error correction. An intelligent algorithm monitors cell degradation patterns in real time. By dynamically shifting the read threshold, the AI precisely compensates for voltage drift, ensuring data remains readable despite physical degradation. Thermal management is a critical aspect of SSD design. High-speed data operations generate significant heat, which can lead to performance throttling if not dissipated efficiently. Components inside the SSD, specifically the controller and NAND flash, act as heat sources. During intensive tasks, the temperature rises significantly. Advanced thermal solutions like heat spreaders conduct heat away from these components, maintaining stable operational temperatures even under heavy load. In edge computing, SSDs face extreme environments, operating reliably from freezing -40 degrees to scorching 105 degrees Celsius. Historically, HDDs were the standard for storage, acting like a library where a librarian must physically retrieve books. Today, high-density SSDs have digitized that library, providing instant electronic access. By 2026, the price per gigabyte gap between SSDs and HDDs has shrunk significantly. High-density QLC memory has made SSDs economically viable for nearly all active data storage. As a result, HDDs are being relegated strictly to cold, deep archive storage, while SSDs have become the dominant choice for all performance-critical infrastructure. As we stack NAND memory to 400 layers and beyond, the manufacturing process faces a sustainability hurdle: the creation of deep, precise holes known as vias. Traditionally, these deep vias require massive amounts of energy for etching. The industry is now evolving toward high-precision plasma processes that reduce energy consumption and chemical waste. By optimizing the gas flow and plasma stability, semiconductor manufacturers are significantly shrinking the carbon footprint per wafer. This efficiency is critical as demand for dense AI storage continues to grow. Hyperscale data centers, like those managed by Meta and Google, have undergone a massive transformation. The mechanical era of hard disk drives is being replaced by the speed and density of solid-state drives. Unlike mechanical disks that rely on physical movement, SSDs provide near instantaneous access. This allows modern infrastructure to handle the massive input and output demands of current AI workloads. As cost and capacity gaps continue to narrow, mechanical drives are being relegated to deep, cold archives, making SSDs the primary foundation of modern global computation. Compared to traditional hard disk drives, which rely on delicate, spinning magnetic platters and mechanical read-write heads, SSDs are built entirely from solid-state electronics. This lack of moving parts makes SSDs inherently more robust. Because there are no mechanical arms to be jarred, they are far more resistant to physical shock and accidental vibrations. In summary, by eliminating mechanical components, SSDs provide superior durability, ensuring your data remains secure even in mobile or high-impact environments. SSD technology has evolved from simple storage to the essential backbone of our digital infrastructure. Today, lightning-fast electronic storage powers the massive datasets of AI models, high-fidelity gaming experiences, and the complex demands of global enterprise. As we move into an era defined by instant data access, SSDs remain at the heart of our electronic future.